there's this. All right, I guess we'll get started. So the plan for today is to finish off this array-based list implementation by showing you how to implement a version of toString two different ways. One of them is a lot nicer for the, well, you'll see that there's a trade-off between the two different implementations. Then I'm going to show you how to compile this program and actually run it. Because this one's a little bit different. So we have a program now that's made up of more than one C file. And a typical C program is actually made up of many C files and many header files. And so compiling those types of programs, you don't want to have to compile them by typing into the command line every time. So I'm going to show you a utility called make that can be used to automate, simplify, I guess, the build process. All right, so step number one, let's implement toString. So this version of toString is a version of toString which will actually try to allocate an array of character, fill in the contents of that array with a string representation of our list, and then return that array of character, the newly allocated array of character, back to the caller. All right, so this one's going to try to do all of the work for the caller. You're going to see that this has a fairly large trade-off in a moment. OK, so I'm going to return an array of car. So there's my return type. Right? This version of the function is called list toString. Right? And it's going to take in a it's going to take in a pointer to a constant list, right? Because toString should not modify the list. All right. So if the list is empty, I'm just going to return the square. So the list I'm going to return is the same as a Java list. It has square brackets, and then it has the elements inside, separated by commas and spaces. So if the list is empty, that's easy, right? If the list is empty, you just malloc an array of size 3, right? You really should check if that's succeeded. So if not s, return null, right? So you really should do that. Wait, return null. There we go. Right, so you really ought to do that. Right? Now, if s was allocated successfully, I'm just going to print two brackets, right? The opening and closing square brackets into the array s. Right? So I'm going to use sprintf to do that. Now, sprintf is basically printf, except the first argument is the string, or is the character array that you want to print into. Right? Now, notice there's something subtle here. Right? Up here, I allocated an array of size 3. Right? But here, I'm only putting two things into the array. Right? So the array looks like it's one bigger than it needs to be. But you have to remember that in C, C expects strings to be terminated with /0. Right? So they want the character /0 at the end of the string, and that's how C determines where the end of a string is in a character array. Right? It looks for /0. Right? Now, sprintf will print that /0 for you if your array is big enough. Right? So up here, if I had allocated an array of size 2, and then called sprintf, well, sprintf will put the two square brackets in, but it won't put the null terminator. Right? So that string that's returned back to the caller will be missing its null terminator, and that will cause a lot of the standard C string functions to break. Right? It'll probably also break your caller's code as well, right? Because they're also expecting the null terminator to be there. All right, so that's easy. Now, it's much harder to fill in. It's much harder to generate the string representation if it's not the empty list. Right? So problem number one, I don't know how big a buffer to allocate. Right? I don't know how big the returned character array has to be. Right? Because I don't actually know what elements are in the list. I have to look at every element in the list, and then I got to figure out how big is this thing going to be. Right? So what I'm going to do is the following. So the first thing I do is I allocate a temporary array of size 100. Right? Now, why am I doing this? Because I need to know what is the integer value that takes up the most number of characters. Right? How long is that? Right? You can't just put in a constant here, because depending on the machine you run on, int max and int min will have different values. Right? So remember, the C standard doesn't guarantee what int min and int max are. They just say that int has to have some minimum size. Right? So you don't actually know how long is the longest integer that you can print. Right? So you have to compute it, which is really inconvenient. Right? Anyway, the longest integer that you can have when you print it out is int min, right? Because it's got a minus sign in front of it. Right? So I need to find out how long that is on my computer. It turns out it's 11 characters long, I think. Right? And then I need to ask, well, OK, so once I print that, so I'm going to print that into my temporary buffer here. Right? Now notice that temp has automatic allocation. Right? It has automatic lifetime here. So that array is going to go away at the end of this function. So I don't have to worry about freeing this array. Right? Now, how long is that string? Well, there's a method called, a function called string strlen, which will return the length of a null terminated string. Right? So that'll tell me how many characters are in the string, right? Not including the null terminator. So I now know what is the longest int that I can print, how long the longest int is when I print it. Right? And now I can go ahead and conservatively estimate my buffer size. Right? So the buffer is going to be, I can conservatively estimate how long the return string needs to be. Right? So how long does the return string need to be? Well, it needs to be max int length times the number of elements in the list. Right? So max int length times the size, but don't forget, I'm going to have a comma and a space between every element. So it's max int length plus 2 times the size. Right? And then don't forget, I'm going to have a square bracket at the front and the back. So there's another plus 2. Right? So that's not an exact estimate of how long the return string is going to be, but it's going to be a conservative estimate. Right? So for sure, the return string is no longer than that. Right? And now, on the next line, oh, so now I can allocate my buffer. Yes?
Would there be no space for the null character at the end there?
There's enough room here. So I got sneaky here, and I added 2 to everyone for the comma and the space. Right? But there's one less separator than there are elements in the list. Right? So there is enough room for the null terminator. Right? So that was fun. Right? OK, now what do I have to do? So I'm going to use printf or sprintf to print into the character array. Right? Now sprintf takes a pointer to the element in the array where you want to start printing from. Right? So it takes a pointer to a car. And so as I fill in this buffer, right, okay, so here's my array of car. Right. Okay, now as I start to fill in this buffer, I need to know where do I end up in this buffer after I print each element into the buffer. Right? Because I can only print the things in one at a time. So I need to print them in one element at a time. So the first thing I'm going to do, if I'm at this location, if I reach this point in the code, I know there's at least one element. Right? So I'm going to use sprintf to print the square bracket. Right? And then I'm going to print the value of the element. So let's say it's 100. Right? All right, so this is going to be my pointer p to begin with. So there's p, right? So I make a pointer up here, right? So car star p is equal to s, so it points to the front of the buffer, right? I print the first element into the array, right? There's no separator here, right? I'm just printing the first element. sprintf tells you how many characters it wrote into the array. So sprintf tells me it writes 4 characters into that array, right? Which is great, because I need to advance this pointer to here so that when I print the next element, it's going to start printing here. Right? So that's what p plus equals 4 does, or plus equals n does. Right? So p plus equals n advances my pointer to the next free spot in that array. And now I've got my loop. Right? So I've got a loop now. And now I'm going to, for every iteration of the loop, I'm going to print a comma and a space and the next element. Right? So the next iteration prints a comma, then a space, and then the next element. So let's say that's -2. Right? And we use sprintf to do that. Right? Sprintf tells me how many characters did it print. So it tells me 1, 2, 3, 4. Right? So I advance p again. Right? And now you just continue, right, all the way till the last element of the list. Right? You just repeat this process. Right? And then finally, when I get to the end, I can just print in the last, the closing square bracket. Right? And then now I can return my array S. Right? If you want to, right? So this estimate of the size of the array is really conservative. Right? The only way you can get an array of that length is if every element is minus int max, is int min. Right? Which is pretty unlikely. It could happen, but it's pretty unlikely. Right? So that estimate of the buffer size is very conservative. So it turns out that the length of S, the capacity of S is probably way too big. So if you wanted to, before you return S, you can realloc S. Right? So if you call reallocate on the pointer S, it will shrink the amount of space that's occupied by the string. Right? Well, you have to figure out how long the string actually is. Right? So call string length down here to figure out how long the string is. Add 1, and then call realloc with the length of the string plus 1 time, plus the length of the string plus 1. Right? And that will shrink the array size down. Right? So if you wanted to, you could do that here. So realloc here, if desired. Right? And that's how you generate a string in C. Right? Good times, good times. So that's, that's much longer than the corresponding toString method than you'll find in the list in any implementation of list in Java. Right? So when Java prints stuff, or when Java generates strings, internally it's doing something like this to figure out how long every string needs to be. Right? If you actually step through with the debugger in Eclipse, you step through a system.out.println, and you print an integer, you'll see it goes through many, 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 many methods to actually print something. And that's because internally it's doing something like this to actually generate the string. Right? All right, so that's string version number 1. Now, let me go to the demo. I've got a little demo up here, which is also on the web. It's also on OnQ now. So in the demo, I'm going to make an empty string. An empty list. Right? I'll make an empty list. Right? I'm going to call list size to get the size of the list and print that out. Right? I'm going to call add 15 times. So I'm going to put 15 elements into the list. Right? If this works, then that will check if my reallocating the array every time to expand the array size is working. Right? Then I want to print out the list to see that it's actually correct. Right? So I'm going to call list to string. Right? And pass in the list. Now remember, list to string allocates a new array every time. Right? So when I'm done printing the list, I have to free that pointer every time. If I don't free that pointer, right, every time I call list to string, I end up allocating a new chunk of memory for the new list, for the new string, and I never get rid of, or I never release the memory that was allocated for the previous string. Right? So with that missing, if that free is not there, you end up with a memory leak. And if you print out the list enough times, you'll eventually run out of memory. Right? Or if you print out very long lists, you'll eventually run out of memory. Right? Now this is really inconvenient for whoever's printing out the list. Right? They're calling your function every time, and then they have to remember to free that character buffer every time. Right? And failure to free the buffer ends up in a memory leak, which isn't good. Okay, so this is, let's just try running this thing to see if it actually works. So it actually does a bunch more stuff. It then removes some elements, then it inserts some elements, then it removes some random elements. Okay, so it's actually going to do a bunch of stuff, but let's just see if this works. And I'll show you how to compile it later on. Okay, what's it called? List? Yeah, there we go. OK, so it looks like it works. Right? So size is 0. We add 0. The size becomes 1. The list looks like that. Right? Add 15 elements. It looks like that. Right? So everything looks like it's working, more or less. It looks like it prints correctly, which is good. Right? But now I want to get rid of this issue of forcing the caller to deallocate that car array every time. Right? So instead, I'm going to provide a second toString function. All right, now this toString function has a different parameter list. Right? It's still going to take in a constant list. Right? But this time, the caller has to provide a buffer or a string. They need to provide me a car array for the function to print into. Right? So now the caller is going to allocate an array. Right? They're going to give me that. They're going to pass the array to the function, and the function will fill in the array for them. Right? So this way, the caller can recycle their array every time they call toString. Right? They just call toString with the old array. Right? If they want to copy the string, they can copy the string. That's fine. Right? They're responsible for that. Right? So this function is no longer responsible for allocating memory for the string. Right? Now, if they're going to pass in a character array, I need to know how big that character array is. Right? So they're also responsible for telling the function how big is this character array. Right? So it's very common to call these arrays of storage buffers in C. Right? So I'm just going to use the word buff, B-U-F, and I'm going to use buff size to indicate the size of the buffer. Right? OK, now what is this thing going to do? So what's this function going to do? It's going to generate the string representation, right, of the list, but it will not print more than that many characters minus 1 into the buffer. Right? Because if it prints more than buff size characters, it will overrun the buffer. Right? And you'll end up, if you're lucky, you'll end up with your program crashing. Right? If you're unlucky, you end up blowing over some other information somewhere. Right? So this function will not print more than buff size minus 1. Right? It won't print more than buff size minus 1 because it's going to put the null terminator at the end as well. Right? It's then going to tell the caller how many characters did it put into that buffer. Right? So we have to keep track of a bunch of information now. There's a bug in this function, which I will let you find. Right? So I'm not going to tell you what the bug is, but there is one. All right, so if the buffer size is 0, I can't do anything. Right? I don't have an array to print into, so I'm just going to return 0 and tell the caller that I didn't print anything into your buffer. Right? Because your buffer has size 0. So that was easy. All right, now how many characters am I willing to write? Well, I'm willing to write that many characters into the buffer. Right? OK, what's nbuff? So nbuff is the total number of characters that I've written into the buffer so far. Right? So that's going to be 0. I'm going to print the square bracket and the first element into the buffer. Right? And now I'm using this function called snprintf. Right? So snprintf is just sprintf. So it prints into a buffer, but it will print no more than how many? This. Right? It will print no more than that minus 1 characters into the buffer. Right? So snprintf is sometimes called the safe version of sprintf, even though it's not really safe. Right? Because you have to tell it you can tell it how many characters to stop. You can tell it the maximum number of characters to print into the buffer. Right? Now, snprintf is very strange in its return value. It doesn't tell you the number of characters it prints into the buffer. It tells you the number of characters it wanted to print into the buffer. Right? So it won't print it more than that minus 1 into the buffer. Right? So it will stop after printing buff size minus 1 characters into the buffer. Right? But the number that it returns is the number of characters that it would have printed if that restriction wasn't here. Right? So if buff size was 5 and you tried to print something of length 10, it actually returns 10. It doesn't return 5, which is kind of weird, but that's just the way it works. So you have to be aware that it's returning some funny value. right? It's not returning the actual number it printed, right? It's returning the number that it wanted to print. All right. Now, if it actually prints that many characters, that's fine. It's the number of characters it printed, right? But if it doesn't print that many characters, then the value that it returns is larger than the value that it actually printed. Okay. So I'm going to add n to nbuff, right? So remember, nbuff is the number of characters that have been printed, right, into the buffer, right? I need to check, right? Is nbuff greater than maxbuff? Is nbuff greater than the maximum number of characters I wanted to print, right? If it is, I'm done, right? Because snprintf always includes the null terminator in the string that it prints, right? So I'm done, and I return that value, right? Because that's the number of values that I put into the buffer. Okay, now it looks a lot like the previous slide, right? Okay, so if nbuff is not bigger than the maximum number of characters I wanted to print, right, then there's still room for me to print stuff into the array. Right? And that also means that n's actually the right value, right? So n actually is the number of characters that were put into the array. Right? So now I can add n to buff, right? Where buff is the pointer, right? So no longer called p, right? So on this implementation, this is now buff. Right? So if n is 4, then buff moves over 4 positions into the array. Right? And now everything else is more or less the same, except I'm using snprintf instead of sprintf every time. Right? Each time you print into the buffer, right, you have to check, right, is the number of characters that I put into that buffer, is that bigger than the number that I was willing to put in the first place? Right? If it is, you're done. Right? So you've run out of space, and you return the number of characters that you put into the buffer. Right? So it's almost the same as the previous one. It's just now you're using a different function. Right? You're using snprintf to do the printing. Right? And I'm always using snprintf here because I need to know how many characters to put in the buffer, and I want to make sure that whatever is at the end of this buffer, if the list ends here, I need to make sure that that's there. Right? And sprintf won't do that if you run out of space in the buffer. Right? So sprintf, if you run out of space, it'll fly off the end of the buffer, and it won't put the null terminator there. Right? Okay. Now, how do you use this version? All right, so for this version, that's down here at the bottom. Right? Now, to use this version of the function, the caller allocates their own array of own array of car. Right? So they make their own array of car, and they just recycle that array every time. Right? So here I'm going to pick a random element from the list to remove. Right? Then I'm going to call remove. I'm going to then generate the string version of the list, right? Dumping everything into the array buff. Right? And then I'm going to print the array, the list that way. Right? And so we've already run this. So this is at the bottom here. Right? So when you start out, it's going to insert 15 elements here again, and now it's going to remove a bunch of random elements every time. Yeah, no, okay. Right? That line is wrong. Right? So remember I told you there's a bug in that second version of toString, and that's the line that indicates where the bug is. Right? So when you remove the last element, you should get the empty array, and you don't. Right? You get something else. All right, so that actually does work. Now, what do I want to do here? I want to make that buffer very small. Right? So if that buffer is very short, so it's only 32 now, it won't be able to show the whole array. Right? If I've implemented list2string2 correctly, right, I will not get an error. Right? So the program's not going to crash. I'm not going to get a segmentation fault or something else weird happening. Right? Because this thing here is only going to print at most 31 characters into the buffer. Right? It'll never blow up that buffer. Right? Okay, so let's see if that works. Okay, so this is how you compile this thing. I'm going to use a program called make, right, which I'm going to explain in a moment. Oh, hey, there we go. other capacity. So this, there's a bug when I fixed this the other day. So, I fixed the version of this function of list.c online. So you have the correct version now. So this is other that. Okay. Okay. So I'm going to use a program called make. Make's going to build the program for me. Right now, when I run the demo, right? Remember my buffer is only 32 characters long, right? So when list2string2 prints into that buffer, right, it stops printing when it fills up the buffer, right? So in this case, right? So that string here that it generates every time is only ever at most 32 characters long, right? So it stops printing and does not blow up or go past the end of the buffer every time, right? All right. Yes?
How can that work?
Why does it work?
So if you look at SN
Yep.
every time you have a pointed buff,
Yep.
buff size. But buff size never gets smaller.
Do buff size.
I assume SN prints buff size characters from the pointed buff. But buff keeps moving forward, and buffer size never gets smaller.
How does this work? That's a good question. I was sure this. That's actually not the bug. Well, that's not the bug that I found. Buff size. Oh yeah, that's because that's const. That's right. How does that? Yeah, that shouldn't work, should it? I guess I have to fix this too. Or it does actually work. There was, yeah, so the way this was originally written, I was decreasing buffer size every time. But you run into a different bug if you do that, which is kind of fun. That really should decrease that every time, shouldn't it? All right, let me fix this and I'll report back with the correct version. Why does it, but this should bomb every time, shouldn't it?
I think it's because the number of characters you print out will never be greater, like, than, there will always be characters at the end that you haven't written to yet.
No, because the buffer size is only 32, so this should blow up. Oh, wait. Yeah, that should blow up. That's a good question. I don't know why it's not blowing up on me. I'm going to have to do some investigating, but that should be going down every time. You are right. Thank you for finding that. That's good. I'm surprised you found that in the lecture. Awesome. All right. So let me fix that, and I will come back to you. But for now, I'm just going to continue. All right. So building this program. I'm going to compile it for you manually. OK. Right. So I've got, to build that program, right, I've got list.c, which needs to be compiled. Right? List.h does not need to be compiled. Right? List.demo does need to be compiled. OK. Now, when you compile a C file in, with the compiler, right, the way we've been doing it so far is we've been writing something like gcc x.c -o x, right, which is fine if you've got one file that you want to compile, and it's got a main method in it. Right? If x.c doesn't have a main method in it, and you try to write this, the compiler will flag an error. Right? So what you really want to do every time when you compile, well, not what you can do every time you compile a file is not produce an executable. Right? So instead, you can direct the compiler to produce an object code file, right, which is an intermediate result to build the executable program. So you can use the flag -c to tell the compiler to compile the file into an object file. Right? So if I do that, right, it will go ahead and compile list.c, and it generates this file called list.o. Right? So list.o is the compiled version of list.c, right, in a format called an object file. It's not an executable file. So to build the executable file, right, you have to link it to some other compiled file that contains a main method in it. right? And so for me, right, that file is going to be listdemo.c, right? So once you've got the compiled version of list.o, you can go ahead and do gcc listdemo.c, right? But I have to tell the compiler that it needs to link to list.o, right? Because list.o is part of this executable program, right? And then you can dump out listdemo as the executable program, right? So that works fine, right? You have another choice here, right? You can instead tell the compiler to just generate the object code for listdemo.c. That also works fine, right? And if I list the contents of my directory now, right? So there's listdemo.o, right? There's list.o, right? Listdemo.o, that's the object file that's got the main method in it. So now I can tell the compiler to link those two things together. Right? So listdemo and listdemo.o, list.o and listdemo.o, and now I can dump out listdemo. Right? So you have to do a little bit of extra work here when you're compiling a C program that's got more than one source code file. Right? There's another issue here. Every time I change something in list.h, right? So if I change the header file, right, then list.c needs to be recompiled and listdemo.c needs to be recompiled, right? Because both of those files depend on the header file. Right? So if I make changes in the header file, I have to recompile every file that depends on the header file. Right? And then once I do all that, I have to relink everything back together again. Right? As soon as you have more than 2 or 3 or 4 files, this becomes a real pain in the butt to do manually every time. Right? And so that's where make comes in. So make's a build automation tool. It's an old build automation tool. So it comes back, it originates from the very early days of Unix. Right? If you have time, you should look at the Wikipedia page and read about the history of it. There are numerous interesting facts and quotes from the creator in that Wikipedia page. In particular, the first version of Make was basically built over a weekend. Okay, so it automatically builds programs and or libraries from source code files. Right? And so the way this thing works is, it's very simple the way this thing works. It just reads in a text file called a make file. Right? The make file tells make how it should build the program. Right? If you click that link, that will take you to the documentation for the GNU implementation of make. All right, so what does the make file do? So to run make, you need to make a make file. Right? And what does the make file do? Well, the make file tells make what to do. Right? So in a simple make file, all that it consists of are a bunch of rules. Right? And the rules are very easy to write. Right? So there's something called a target. Right? Then there's a colon. And then there are the prerequisites. Right? On the next line, there's a tab right there. Right? That has to be a tab. Okay? So the stuff in red, that's important. Right? So every recipe step has to start with a tab, not spaces. Right? If you put in spaces here, make won't work. Right? It won't actually run the recipe. I think it actually says there's an error. Right? If you read the Wikipedia page, there's a comment about the tab. Right? It's called probably the worst mistake that's ever been made. Right? So putting a tab there turns out not to be a good idea because everybody puts in spaces and then they realize it doesn't work. Right? All right. So what are the prerequisites? The prerequisites are just the files that the target depends on. Right? The recipe is just some command that knows how to build the target. Right? And you can have multiple lines in the recipe. Right? You can have as many lines as you want. All right, so what does this look like? So in a makefile for a simple C program like the one we just created, right, the very first rule in your makefile can define how to build the final executable program that you want to build. Right? So make calls the first target the default goal. In other words, that's the thing it's going to try to build if you don't tell it to do something else. Right? So the prerequisites, those are just the dependencies. Right? What does the target depend on? The recipe is just the commands needed to build the target, given that the prerequisites have already been built. Right? So how does this look, what does this look like? Whoa. The complete, why is this? Oh, here's I see, here's hello.c. So this is the hello world program. This is the make file for the hello world program, right? So the hello world program, way back, I think the Friday before reading week, right? We made a program called hello1, right? So that's my target, right? That's going to be my executable program. What does it depend on? Well, it only depends on that one source code file, right? hello1.c, right? How do you build hello1? Well, you just run the compiler, right? So gcc hello1.c minus o hello1, right? So what does that makefile say? Well, that says hello1 depends on the file hello1.c, right? If you change hello1.c at any point in time, right, and then rerun make will rebuild hello1, right? So in other words, it'll run the recipe for hello1, right? And so it'll rebuild your file. So what that really means is, if this file, if any of the dependencies or prerequisites are newer than the target, then make will rebuild the target, right? So it's a very simple way of keeping track of how, if changes to any of the files in your program have been made, right? So if that's newer than that, then it will try to build the target, right? Okay. So the start, for our list demo program, right, our makefile might look like this. It doesn't have to look like this. You could write it many different ways, but it might look like this. Right? So what does list demo depend on? Well, it depends on the object file list.o and listdemo.o. Right? Now, why am I not saying listc and list.h and listdemo.c? It's because I'm going to put in separate rules that define how to build list.o and listdemo.o. Right? Now, if these two things exist, right, and they're newer than that, then the recipe will be run. Right? So how do you build the final program? Well, it's just link these two object codes files together and generate the output file listdemo. Right? So that's it. So that's the start of our makefile. Right? Okay. Building the prerequisites. Okay, so in most C programs, one or more of the prerequisites for the overall target also need to be built, right? So back here, right, I may have to build list.o and listdemo.o, right? So if they don't exist, they need to be built, right? And so you can define a rule to build all of the prerequisites as well. Right? So what does list.o depend on? Right? So what does the object code for list.o depend on? Well, it depends on list.c and list.h. Right? If one of list.c or list.h changes, right, then list.o will be rebuilt using that rule there. Right? What does list.demo.o depend on? Well, it depends on listdemo.c and list.h. Right? It depends on list.h because it includes that header file. Right? And I'm the one that's actually writing the header file. Right? So if I make changes to list.h, I probably have to rebuild the object file for listdemo. Right? So if one of these two files changes, then this target gets rebuilt. To run make, you just type make. Right? So if you've got GCC or CLang installed on your computer, make's already there. Right? So to build the default goal, just run make. Right? And what does make do? Well, make reads this makefile. Right? It tries to build the default target. Right? So it tries to build the first target in the makefile. Right? It looks at the dependencies. Right? So it says, oh, this program depends on list.o and listdemo.o. Right? If these two files are not, So when it sees these two dependencies, right, it does not automatically run that rule. Right? So what it does is it says, oh, well, how do I make list.o? It finds the rule for list.o. And it says, oh, well, this depends on list.c and list.h. Right? It then looks for, are there rules for list.c and list.h? And the answer is no. Right? So now it says, OK, is list.c or list.h newer than list.o? If the answer is yes, it runs the rule. Right? And it builds list.o. Right? It does the same thing for listdemo.o. Right? So listdemo.o depends on listdemo.c and list.h. Right? If one of these two files is newer than listdemo.o, it runs, sorry, there's no rule for listdemo.c, there's no rule for list.h, right? So if one of these two files is newer than that, it runs the recipe and builds listdemo.o, right? Now it comes back up to here, right? If one of these two files is newer than listdemo, now it can run that rule, right? So all make is doing is it's looking at the dependencies that you told it exist in your program, right? Rebuilds anything that depends on those dependencies, and then, if necessary, rebuilds the final target. Right. Okay. So I just told you that, if the target already exists. All right. So in this make file, the way it's written anyway, right? If I touch list.h, right? So I don't even have to modify it, right? All I have to do is write touch. I just have to run the touch command, and that will update the modification time on list.h, right? So I touch list.h, right? Then list.o will be rebuilt, listdemo.o will be rebuilt, and then listdemo gets rebuilt, right? So for example, if I touch list.h, let me sort by time, right? So notice that list.h, that's the most recently modified file, right? If I've written my make file correctly, make will rebuild everything, and it does, right? So it recompiles list.c, it recompiles listdemo.c, and then it links the two object files together. Right? Yep?
List.h isn't one of the dependencies on listdemo, though.
On listdemo? Yeah, but listdemo depends on list.o and listdemo.o.
So like the cursor goes.
Yeah. Yeah. So when it rebuilds list.c, sorry, when it rebuilds list.o, right, because list.h changes, right, list.o is now newer than listdemo, right? So now listdemo has to be rebuilt, right? Because
something that wasn't parsed, like if you had some object that wasn't used by listdemo.
Yep.
And it depended on list.h, would it rebuild?
Yeah, it would rebuild that, but it would not. Sorry, no. So that would not happen. Okay, so if you're for a simple makefile, if the default target does not list a dependency, right? So for example, suppose there's a.o somewhere, right? So there's a file a.c somewhere, right? And you've got a rule for a.o down here, right? If a.o doesn't appear in this line, then then the demo will not be rebuilt if only a.o changes. Yeah. You wouldn't. That would not normally. So in that should not normally happen because you've listed a dependency that doesn't actually exist. Right, so you've actually got a buggy makefile. That's the problem with make. Make's not smart at all. Right? Make believes what you told it. So if you've got errors in your makefile, your build's busted. Phony targets. Actually, this is related to your question. So a phony target is one that's not is a target that's not the name of a file, right? So back here in my makefile, right? List demo, that's the name of the executable program that I want to generate, right? So that's the name of a file. List.o, that's the name of an object file. And listdemo.o, well, that's the name of another object file, right? So those are all file names, which is usually what happens in a makefile, right? But you're allowed to specify a target that's not the name of a file, right? Now, if it's not the name of a file, make will never build that target, right? Because make's always looking for things that are newer than the target, right? If the target's not a file, it doesn't know how new the target is, right? It doesn't know the age of the target, so it doesn't build it, right? So these phony targets, they're not files. It's just the name of a recipe that you might want to run at some point in time, right? So to build a phony target, you tell make to specifically build that target. Right? So you write make target, where target is the name of the phony target. So one of the targets that you normally see in a makefile for a C program is something called clean, right? Clean is just the target that you want to build when you want to basically rebuild your project from scratch, right? So if I wanted to rebuild listdemo completely from scratch, right, I want to remove all the object files and the executable program listdemo, right, which you can do with the command rm, right? So remove listdemo and star.o. So if I run make clean, so hang on. Right, so there are all my files. Right? If I run make clean, it's going to remove, right, all of the object files and the executable file. Right? Now if you run make again, it'll rebuild everything again. Right? And there you go. Right? So make.clean is it traditional? It used to always show up in make files for C programs. It doesn't always show up. So the problem with make is, like I mentioned, it's not very smart. So if you have a very complicated make file, it's easy to screw up the dependencies. And when you do that, if you try to rebuild your program, it won't work because something that should have been rebuilt isn't rebuilt. Right? And so that's one situation where you might want to run make clean. Right? So you want to nuke everything and rebuild everything from scratch. Right? It's basically the target of last resort. Right? Because if you run into that situation, there's something wrong with your make file. Right? But you can find examples of extremely complicated make files. So those ones almost always have a clean option in it. Right? So that's an example of a phony target. You can put in other phony targets if you like. That's probably the most common one. All right. What else do I want to do? Did we try touching? Yeah, we did that, right? So we touched the header file. We saw that it rebuilt everything. So I think that's everything. Right? OK, so you're now ready to start building moderately small, well, still small, but moderately, but more complicated C programs than just a single C file. Right? So moving on, you're going to have to start writing some make files for any of the assignments that you're doing. Right? Not the next assignment, not the current assignment, sorry, but assignment 5 and 6. You'll either have to run a make file or write your own make file to generate the final executables. All right, so I will address your question and see if I can figure out what's going on. And other than that, we're done for today.